All right, cool. So, section's recording. Welcome to section 2, everybody, for CSE 373. Today, we're going to be covering algorithm analysis. So, I'm going to go ahead and share my screen. All right, cool. Now I do that thing where I ask, can everybody see the screen?
Yeah.
Awesome. Dope. Admit some more people in the waiting room, and let's start the slideshow. And for those just coming in, I just want to reiterate, section is recorded. If you prefer not being in a recorded section, there's a section, in-person section at 1:10 during this time. There's also another virtual section at 10:50, or you could just watch the recording after we upload it. But cool. So we're going to be talking about algorithm analysis, kind of like building on what we were talking about in lecture. And on the bottom right of this slide, we have some big O notation, very common big O notation. O of 1, that's like equal to, oh yeah, like that's nice. That's like as fast as you can get. That's constant. No matter how big your input size is, it's always going to have the same runtime. We like O of 1. So we're like, oh yeah. And then O log of n is the next fastest runtime. It's nice. It's not incredibly fast because it still grows as n gets larger, but it's still like really nice. O log of n is really nice. O of n, this just means that as your input n gets larger and larger, the runtime will grow linearly. So it's pretty okay. It's O of okay. On squared, your runtime is gonna run, it's gonna follow like a parabolic shape. So it's going to grow, what's that math term? In a squared manner. So if your input size is like 2, it's gonna be a runtime of like 4. And as your n gets larger, your runtime is going to grow much faster. So it's getting a little bit slow. Oh my. And then next up, we have exponential runtime, O2 of n. That's super slow. That means your program's runtime is growing at an exponential rate. So you want to avoid that at all costs. And then one of the like slowest runtimes you can achieve, to be honest, I can't even think of a runtime that's like an algorithm that runs in n factorial. But this is like super slow. It's like, oh my God, try to think of like something else. Try to optimize the algorithm a little bit. But cool. Let's first go over some administrivia. So P1 Dex is out. It's going to be due next Wednesday, July 6th at 11:59 p.m. And again, you can have partners for all the projects in this class except P0, but that was already due. So going forward, you feel free to establish your groups. I think you can have groups of up to around like 3 people, I believe. But yeah, in this project, you're going to be implementing a double-ended queue. And this is just going to be like a normal queue, but you can add and remove from either the front or the back. So typically with a queue, you can only add from the front and you can only add to the back and remove from the front. But in this double-ended queue, you can do either of that in either the front or the back. And to get you with practice of understanding runtime and understanding like how one implementation is better than the other, you all will be working and implementing multiple implementations of this, allowing you to reflect and think about the pros and cons of each. Like what happens if we implement like a linked list compared to if we implement it with an array? Either way, all these implementations will achieve the same result of a deck, but it will have different runtimes, which forces you to think, all right, when should I use this implementation versus this other implementation? And in this section, we're going to learn all about runtime, which helps you think about this concept a lot better. Other than that, office hours are up and running. They can be found on the course website or on Ed. My personal hours are going to be on Fridays, 6 to 8. So if you have any questions or just want to come say hi, come through. It's going to be the same link as today's section, but you don't have to remember it. It's also going to be on the ad announcements and all that. All right, cool. Any questions about administrivia? feel free to raise your hand, drop a comment in the chat. Awesome. Cool. So let's start off with a micro teach about basic big O. So kind of reviewing what I talked about earlier. These are the main different complexity classes. We have constant complexity, logarithmic, linear, log linear, quadratic, cubic, some extra ones that we don't really cover, and then exponential. And one thing that's missing is n factorial, but very, very, very rarely are you going to implement an n factorial algorithm. So going over these complexities a little bit, constant runtime, it just means that as your input size gets bigger and bigger, your runtime is always the same. So an example of this, other than the example they gave, is let's say you have an array of size 4 or something. So actually, just to make it easier to draw, let's say we have an array of size 1 or 2. An example of a constant runtime is trying to access the first element of this array. No matter how big this array gets, so let's say I have like 0, 1, and I have 0, 1, dot, 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 like 10 million or something. So an example of a constant runtime kind of like algorithm or access is trying to get the first index of an array. Notice that no matter what the size of the array is, whether it's size 2 or if the array is size 10 million, accessing the first index always has the same runtime because I can just access the value at index 0. So no matter how big the input gets, no matter how big n gets, accessing a value at an index is always constant. So it's O of 1. The next example is logarithmic time. So logarithmic time, it's the next fastest complexity class that we'll be working with. So logarithmic time, it kind of like grows really slowly, which is good. So that means as your input size n gets larger and larger, the runtime only is going to increase slightly. An example of this is binary search. And why is that the case? Well, in binary search, let's say we were supposed to guess a number between 1 and 100. So one way you could do this, if I were to tell you if your guess was going to be larger or smaller than your guess, you could use binary search. The way you would do this is you just guess the number that's in the middle. So let's say 50. And then I will tell you from there, the true number is higher or the true number is lower. So if I say the number is lower, then your next guess could be 25. And if I say lower again, your next guess is going to be like 13 or something, and so on. But the idea with binary search is that the possible range of values is halved every single time you guess. So that means you can guess the correct number within about 7 guesses. So that's logarithmic time. So as the input gets larger, so let's say instead of like, I asked you to guess a number between 1 and 100, I asked you to guess a number between 1 and 1000. Then the number of guesses you will need to find the correct answer is just log base 2 of 1000. So as the input gets larger, the runtime does increase slightly, but not that much, because you have the possible range of answers every single time. So each time you go through an iteration, you do half the work. So that's what logarithmic complexity is. And whenever you see something being halved, that usually means it's logarithmic time. Not all the time, though. The next complexity class is going to be linear. So linear, exactly as it sounds, as your input size grows, the runtime grows with it. So using this kind of like search example, if I didn't use logarithmic search, like if I didn't tell you if your guess number was higher or lower, you would have to actually guess every single number, right? Maybe you can start with 1, then guess 2, then guess 3, then guess 4. But either way, you're going to have to guess every single number in the worst case until you guess the correct number. And if let's say we add another 0, let's say I ask you to guess a number between 1 and 1000, then the runtime of this algorithm will grow with the input size. Now you have to guess 1000 times. If the range is between 1 and 10,000, now you have to guess 10,000 times, and so on. So linear complexity class just means that your runtime grows linearly, or it grows with the input size. As input gets larger, the runtime gets larger with it linearly. All right, any questions so far about constant, logarithmic, or linear runtime? All right. So the next complexity class is going to be log linear. So this is going to be somewhere between linear time and quadratic time. So log linear time is, in other words, order n log n, and it slightly more than doubles if you double n. So it grows faster than log linear, meaning it's than linear. So it's a little bit slower than linear time. And an example of this is an algorithm called merge sort. And we'll be covering sorting algorithms later in the quarter. So I won't talk too much about that. But just know log linear is somewhere in between linear time and quadratic time. So it's going to be looking like this graph over here. So it's not super good. It's not super bad. Somewhere in the middle. The next complexity class we're going to be talking about is quadratic. So quadratic is n squared. So whenever you see nested loops, say you have a loop that runs n times and then an inner loop that runs n times, that's quadratic time. That is approaching the runtime where it's, all right, this is a little bit slow. And you might have to start thinking about, can we make this better? But so as your input size increases, the runtime will increase by a factor of n squared. And then cubic, same thing as n squared except n cubed. So think of a triple nested loop. And normally whenever you see like n to the x, so n to the fourth or n to the fifth, you can just think of that as like n number of nested loops. So n quadratic runtime has 2 nested loops, cubic has 3 nested loops, etc. And then one more runtime that we won't really go over too much is exponential runtime. So this is just super slow. Your runtime is going to multiply drastically. Even if you add 1 to your input size, your algorithm is going to run really slow no matter what. So these are the different complexity classes. Whenever we're designing algorithms, we generally want to design our algorithms and methods such that it's O n log n or faster. Sometimes we can't avoid that, and sometimes we have algorithms that are n squared or even like n cubed. But generally, as computer scientists, we want to design faster algorithms, and generally fast algorithms are anything that's O n log n or faster. Any questions about any of the complexity classes, or any questions about the examples, or any examples y'all want to share? All right. So some basic rules before we get started on some problems. So exponential dominates a polynomial. Higher order polynomial dominates a low order one. Any polynomial dominates a log. Log dominates constant. So what the hell does that mean? That basically just means that if a method has a runtime of, say, like O n squared plus n, this dominates just means that you just take the biggest runtime in this runtime function. So in this case, n squared is bigger than n. So that just means that this runtime is in order n squared. So it allows us to like simplify things a little bit. That's what dominates means. So if you see like a exponential and a polynomial, just look at the exponential. That algorithm's runtime is exponential, not exponential plus polynomial. You just take the largest of the two, or the largest function within the function. Any questions about what dominates means or which one's bigger than the other? All right. We clear out these annotations. Cool. So one important thing before we get started on problems, in asymptotic analysis, we don't care, or runtime analysis, we don't care about leading constants or smaller terms. Why? Because all of this assumes n is approaching infinity. So that we're just assuming that n is a very, very, very big number. So constants and coefficients don't really matter too much. So for example, if you have O of like 1000 and n, 1000n, and you have order 1 over 1000n or something like that. Let's just do 100. These have the same runtime. So they're both O of n. So whenever we're talking about runtime analysis, we don't really care about the coefficients or any constants in the runtime function. So order 1000n is the same as order n. Order 1 over 100n, that's just the same as order n. Either way, it grows linearly because we're assuming n is approaching infinity. If n is infinity, this 1000 is irrelevant, this 1 over 100 is irrelevant. Cool. So let's go ahead and get started with some problems. So I'm going to pause recording for a bit. And then I'm going to break you all out into breakout rooms. And then let's see, pause. All right, cool. Resuming the recording and picking up where we left off with question 1A and 1B. All right, so comparing growth rates. So for this problem, first problem, 1A, we're supposed to simplify each of the following functions to a tight, big order bound, big O bound in terms of n. Then order them from the fastest growing to slowest growing. Fastest function means the one that increases the most rapidly as n increases. So this is like super confusing wording, but because if it's a fast growing function, it means it's actually really slow. Because as n increases, that means it gets bigger faster. N grows bigger faster. So that means it's actually slower when you actually run it. But let's go ahead and get started with log base 4 of n plus log base 2 of n. So anyone have any thoughts about this problem? What runtime is this? What's the tight big O bound in terms of n?
Logarithmic?
Yeah, so it's just going to be logarithmic time. So why is this? You might be looking at this and thinking, all right, one of them's log base 4, one of them's log base 2. So like, is it going to be like logarithmic base 4 or logarithmic base 2? But actually in logarithmic time, it's actually just going to be logarithmic, like no base is stated. And why is this the case? Well, because if we actually use some math, if you remember from like calculus, wherever, there's a formula called the change of base formula. We can actually do some math to figure this out. The change of base formula, just to refresh y'all's memory, allows us to kind of like convert a logarithm's base to any number we want. So when we do the change of base formula, it's going to follow this formula where log b is the base that we want. So if we apply this logic, then we can do something like log base 4 of n is equal to log base 2 of n divided by log base 2 of 4. So we're converting this first log into base 2. And now you'll notice that log base 2 of 4, that just evaluates to 2, which is a constant. So it's basically log base 2 of n divided by 2. And we don't really care about just constants whenever we're doing asymptotic analysis, because we just drop constants and coefficients. So we end up getting that log base 4 of n is pretty much the same thing as log base 2 of n after we get rid of constants and coefficients. So this is really just basically log base 2 of n plus log base 2 of n, which is 2 log base 2 of n. But again, we don't really care about coefficients and constants like that. So this is just going to be log of n. What the change of base formula basically kind of like argues for and allows us to assume is that no matter what the base is, it doesn't really matter because we can convert any log into any base. And as you can see, as we went through the math, we just ended up dropping all the constants along the way. So since we can convert any base to any log base to any base, and we end up dropping the coefficients along the way anyways, we never really care about what log base it is. Logarithmic running time is always just going to be logarithmic running time, no matter what the basis is. So the first one is order log n, which is pretty okay. All right, now the next one. So can someone tell me what complexity class this is in?
Linear.
Yep, it's just going to be linear. So we're just going to drop the constants. So we're going to drop the 4. We're going to drop dividing by 2 because that doesn't really matter as n gets to infinity. That dividing by 2 literally just does nothing because it's approaching infinity. So it's just going to be linear running time. So that's still pretty solid. Linear, not bad. And then what about this one, 2 to the n? What complexity class is this?
Exponential.
Yep, it's going to be exponential. And more specifically, it's going to be O of 2 to the n. Again, we just drop the constants. We just drop the 3. Because if you think about it, if n is like 10 trillion, what the heck is this plus 3 going to do? It doesn't really do anything. So we can just drop the constant. And if you noticed, so this is order 2 to the n. This value 2, if it was like 3 to the n, that would be a totally different complexity class. It's still considered exponential, but it's 2 to the n and 3 to the n clearly kind of like grow at very different rates. So this number right here, it's going to be its own complexity class if it changes. So if it's 3 to the n, that's going to be a different complexity class than what it is now at 2 to the n. But either way, it's exponential. All right, cool. What about 750,000? That's a pretty big number. What complexity class is this?
Constant.
Yeah, exactly. It's constant. And why is that? Like 750, oh, not 750,000. This is 750 million. 750 million. How is that constant? That's so like slow, it feels like. It's like a for loop running 750 million times. Well, it's constant because no matter how big n is, it's always going to be 750 million. And in fact, there's actually no n in this function. So it doesn't grow with n. So that means you can have your input size however big you want. The runtime is always going to be the same. It's always going to be 750 million. So it's actually going to be constant runtime. So a little bit trippy because 750 million, that sounds really slow, right? 750 million operations. But this is actually really, really fast, and you can't really get faster than that because the runtime is always the same, no matter how big your input is. All right, what about 8n plus 4n squared? Actually, before anyone says anything, drop your answer in the chat. So type it up, but don't hit enter yet. All right, hit enter in 5, 4, 3, 2, 1. Nice, awesome. Yep, all of you are correct. It's going to be quadratic time. Now, why is it quadratic time? It's because of what we talked about earlier in the slides. Right here. So higher order polynomial dominates a lower order one. So if we go back to this question, we have 8n plus 4n squared. So 8n, that's kind of polynomial. It's polynomial to the 1. But since we have n squared dominates n. N squared grows much faster than n. So we can just drop n, and our runtime is just going to be quadratic, or order n squared, like all of you mentioned. So yeah, and another way you can think about it, just think about like an incredibly big number, like 10 trillion, 8 times 10 trillion compared to 4 times 10 trillion squared. 8n is like nothing. So that's kind of like what we mean by dominate. All right, and ordering this from fastest growing to slowest growing, we have O to the n. This is the slowest growing. If we go back to like a couple slides earlier, you can see that exponential functions grow incredibly fast. Like if you just go from n is 2 to n is 3, it's going to like just skyrocket. So 2 to the n plus 3, this is the fastest growing out of these other functions. Next up, we have n squared. So this is our quadratic function. And then we have O of n, linear, O of log n, logarithmic, and then O of 1, constant. And this is kind of, you can just think of this in math terms. O of 2 to the n, that graph is like super steep. N squared is like a parabola, pretty steep still, but not as steep as 2 to the n. O of n, that's just linear. Log of n is more like a curve. And then O of 1 is just a flat line. So it doesn't increase as your input increases. Now, one thing that's super confusing whenever we use the word like fastest in terms of like runtime, when we say it's the fastest growing, it's actually going to be the slowest runtime, right? Because that means if something is fast growing, it means that the number of iterations you will have to do is going to increase really fast. So that means you can go from like 2 iterations to like 15 iterations super quickly. So if it's slow growing, that means as your input increases, your runtime doesn't really get that much slower. Or yeah. So any questions about this question, or the difference between fastest growing versus like fastest runtime? All right. So let's go to our next problem, 1b. So state a tight big O bound for each of the following functions and order them from the fastest growing to the slowest growing. Fastest function meaning the one that increases the most rapidly as n increases. So what is the What is the big O bound for 2 to the n divided by 2? Anyone have an idea? All right, I'm seeing logarithmic runtime. 2 to the n, square root of 2 to the n. All right, yeah, this one is actually kind of a trick question. So commonly, you might think it's 2 to the n because, oh wait, it's 2 is just a constant, right? So we can just drop it. Well, you can usually drop it, but in the case of exponents, you can't drop the constant. Why? Because it's not really a constant factor. So looking at like some of these examples, the dividing by 2, the exponent actually significantly kind of like changes the runtime. So using this example, we have 2 to the 2 times n. That's equal to 2 to the n times 2 to the n. That's a pretty big jump from just 2 to the n. So the exponent, when we're dealing with exponential runtimes, the constant factors in there actually play a huge role in the runtime and the runtime graph if you graph it. So we can't really ignore that. So what that means is actually kind of like its own runtime. It's order 2 to the n divided by 2. So it's still exponential, but it's a little bit better than 2 to the n. All right, next up, 3 to the n. So what complexity class is this? What's the big O bound for this one? Yep, and I'm seeing 3 to the n. Yep, and you would be correct. So this is going to be 3 to the n. And this is still considered exponential complexity because you're bringing this number to an exponent. But it is different from this next runtime, which is 2 to the n. So both of these are exponential, but 3 to the n grows much faster than 2 to the n. For example, if n was like 2, 3 to the n would be 9, 2 to the n would be 4. If n was 3, then this would be 27, and then this would be 8. 3 to the n grows a lot faster than 2 to the n, even though they're both exponential. So 3 to the n is much slower than 2 to the n, but they're kind of like the same complexity class if you think about it. It's still exponential. All right, any questions on that? Which of these is the fastest in terms of runtime? Any ideas? Which one is the fastest in terms of runtime? Yep, Scott said A, and yeah. Yep, exactly. Y'all are both right. It's going to be the first one. Because this is the slowest growing, even though it's still pretty fastly growing, it's kind of like exponential. It's still going to be the faster algorithm out of these ones, because faster growing means you're going to have more iterations as n gets larger. So since this is the slowest growing, it's the fastest runtime. And then fastest growing, slowest. So 3 to the n, super fast growing, but it's slow. 2 to the n, somewhere in the middle. 2 to the n divided by 2, slowest growing, meaning has the fastest runtime. All right, so now we're talking about these different runtime descriptors, big O, big omega, big theta. So what are they? So generally, when we're talking about runtime, we kind of talk about it in bounds, right? So we have big O, and big O is going to be the upper bound on how quickly a function grows. So informally, it just means less than or equal to. Big omega is going to be the lower bound on how quickly a function grows. So for example, the difference between the two, let's say you have an algorithm that runs in linear time. An upper bound is O(n) squared, because a linear running time algorithm is less than or equal to a quadratic runtime algorithm. An example of an omega bound to in a linear runtime algorithm is log n, because O of n is strictly greater than or equal to log n. And then a tight bound is somewhere in between. It means that it's equal. So you can think of the tight bound as like the perfect function that represents the runtime of an algorithm. And some notes, f being order g is the same as g being omega or big O of f. So f being big O of g is the same as g being omega of f. So why is that? Let me draw it out real quick. So this is just saying if we have two runtime graphs, and this is g, and this is f, it just means that f being upper bounded by g, so notice how g is strictly, or f is lower than g, is the same as saying g is lower bounded by f. Notice how f creates kind of like a lower bound for g. This is basically what this notes is saying. Any questions about these three bounds? All right. So now for a picture to kind of like help us understand it. So when we say big O n log n, these are all the functions that are kind of upper bounded by n log n. So n is upper bound by n log n, constant time is upper bound by n log n is upper bounded by n log n. This just means that n log n is an upper bound for these functions down here. And over here, we see that if we have a omega bound n log n, it just means that n log n serves as a lower bound for these functions up here. So to the n, a lower bound is n log n, and for n squared, a lower bound is n log n. Any questions about big O or big omega? All right. So now how do we get big theta, and what even is big theta? So in order for a function to be big theta, f must be both O big O g and big omega g to be big theta g. You can just think of this as squeezing the function from above and below. So the function f has to be both an upper bound and a lower bound. So it's just getting the perfect fit, pretty much. So now let's do problems 2C, 2D, and 2E. Let's do this together since we don't have too much time left. So, oh, I guess it gives the answer, but that's fine. So if a function is in big omega of n, then it could also be in big O of n squared. And this is true because it's possible for a function to both live below n squared, but above n. So for example, n to the 1.5. So as you can see in this example, so say we have a function that is lower bounded by n. So it has to be above this line right here. It has to be above this n line. But it also must be upper bounded by n squared. So this is just saying there exists a function that is between these two graphs. And that is true because it gives an example right here, n to the 1.5. N to the 1.5 goes right through the middle of these two. So that is true. That is possible. Any questions about this problem? All right. So what about 2D? So for 2D, if a function is in big theta of n, then it could also be in big O of n squared. So that means it's tight bounded by n. And we're trying to figure out if it's possible for it to have an upper bound of n squared. So for it to have an upper bound of n squared, it just means it has to fall below n squared. So for example, in a function, if it is in O big theta of n cubed, then this would be false because n cubed is somewhere over here. And that's not in upper bounded by n squared. But since this function is going to be theta bounded by n, that falls within n squared. So this is true. Any questions about this? All right. So now let's take a look at this one. If a function is lower bounded or big omega bounded by n, then it is always in order n. So this is just saying in order for it to be omega n, that means it has to be somewhere up here. So it has to be slower than linear runtime. But right here, we're saying then it is always in order n. But that's not necessarily the case because it might be the function could be n squared. N squared is in omega n because linear runtime is lower than quadratic runtime. But n squared is not upper bounded by n. N squared upper bounds n, in fact. So this statement is actually going to be false. Any questions about this one? All right. Cool. Now let's talk about problems 4a and 4b. So code modeling. Now that we got some practice with understanding runtime functions and things like that, let's try to understand runtime by looking at code. Let's try to start analyzing code for runtime. So problem 4a, let's do this one together. So we have int x equals 0, and then we have for int I equals 0, I is less than n, and then we have a nested loop for int j equals 0, j is less than n times n, divided by 3. So usually when I see a problem that has a loop in it or has multiple loops, my first intuition is thinking about how many times that loop runs. So I know this outer loop is going to run like n times. So let's make a note of that. And then I look at in the inner loops, and this inner loop runs n times n divided by 3 times. So n squared divided by 3. And then from there, that's when I try to figure out what the runtime is. So based on what we kind of like just listed out and drew out, does anyone know the runtime for this particular algorithm? You can either shout it out or type it in the chat. All right, I'm seeing an n cubed. All right, seeing another n cubed. All right, and you will both be correct. This is going to be n cubed. And why is it n cubed? Because if the outer for loop runs n times, and the work we do inside the outer for loop is n squared divided by 3, and we do the math, we just get n cubed divided by 3. But since the 3 is just a constant, we can just drop it. So this algorithm is going to be an order n cubed. It's going to be a cubic runtime algorithm. So pretty slow. Cubic runtime. All right, now let's talk about 4b. All right, this one's a little bit trickier. I'll give y'all a few moments to think about it, and then let's see what we can come up with. So far we have int x equals 0. That's going to just run one time. This is going to run n times, question mark. And it looks like if it's I mod 3 is equal to 0, we break. So this is kind of weird. All right, what are we thinking? What do y'all think the runtime for this algorithm is? Nice. We got some constant runtimes in the chat. And yeah, y'all will be correct when you say constant runtime. Now, why is this constant runtime? We have a for loop that runs n times, right? Well, yeah, but no. And the reason is because of this condition, this if condition right here. It says if I mod 3 is equal to 0, we break. So we know that this for loop can only ever run, since we only decrement by 1 each time, this for loop will run up to 3 times. So no matter how big n is, if n is like 10 trillion, this for loop will only ever run 3 times. So since it's always like a constant amount of runs, I guess it's like 3 or less, this is actually going to be a constant runtime algorithm. So this is a little bit tricky because, as you can see, we have like a for loop that runs n times, but because of this if statement, we limit how many times we run. So it's actually just going to be constant runtime. All right, so we don't have too much time for this specific piece of section. Ran out of time a little bit, but this section mainly covers mathematical definitions. So kind of like covers how you can like prove a certain runtime is upper bounded or lower bounded by a certain function. But this is the big fancy theorem that kind of like proves this. So if f of n is upper bounded by g of n, then there exists positive constants c and n naught, such that for all n that is greater than or equal to n naught, the function f is less than c times g of n. So if you're like me, and the first time you saw this theorem, you're like, well, what the heck does that mean? I have some good news for you. This big theory, it basically just means that if you plot the runtime of f of n and g of n, if you plot these functions on a graph, then at some point, the function f of n starts falling below g of n at some value n naught. So if we look at this plot up here, you'll notice that this algorithm in kind of like, I guess, purple, I'll just call this purple and pink. This algorithm in purple right here, it does have a slower runtime from 0 to like 35, right? But starting at 35 onward, it's much faster than the pink algorithm right here. So that's what n naught is. So at this point, 35 or n naught, this purple algorithm is upper bounded by this pink algorithm. And that makes sense because this purple algorithm kind of looks like log n, and this pink algorithm looks like n. So even though 10 log n is slower than n with n values less than 35, once we get to 35 and bigger, it's always upper bounded by n. So that's what n naught represents in this. And where does the C come into play? So the C comes into play when we're dealing with something like this on this lower graph right here. So we have 2 log n and log n. We know that both of these runtimes are the same. They're both logarithmic, but this 2 log n makes it look like log n is upper bounded by 2 log n, when really they have the same runtime. So the C just basically means that constants like 2 log n, 10 log n, they don't really matter. That's basically just what C means. And I think that's all the time we have for section today. But I would recommend going through some of the remaining section problems. There's a bunch of there's a bunch of problems for you to practice on. Highly recommend doing some practice on that. And on that note, I'm gonna pause and stop the recording.